Now, another one. Okay, show that, okay, if n squared is even, then n is even. So we assume that n is an integer. So first of all, the theorem is nothing wrong. Okay, this is correct. N squared is even implies n is even. It is correct. But let's look at the proof. So I'll copy the proof. Let's say this is a proof that is made by some other students. So we assume that. So assume that n squared is even. Then n squared is equal to 2k for some k, for some integer k. And then we let n is equal to 2m for some integer m. And finally, thus, okay, so we have finally thus n is even. Full stop. Okay? You see the proof, right? So the proof is we assume that n squared is even, so n squared is equal to 2k for some integer k. Now we let n to be 2m for some m. So n is even. Okay. Something wrong. It looks like something wrong. Okay. Line 3. Okay, very good. What's wrong with it? Yeah, this is something wrong. Now, the first two part doesn't have anything wrong. It's saying something correct. Suppose n squared is even. We can suppose this because we are showing P implies Q. So a good way, one of the strategies is direct proof. So we have n squared is equal to even. And because of this, we have n squared is equal to k. So there's nothing wrong with the first two lines. What is the third line? It says let n is equal to 2m for some integer m. How can you let? There's no reason you can let. Okay, if you can let anything, then I can prove anything. Right? Right? So this is something wrong. This one follows from nowhere. It does not follow from the premise. It does not follow from the axiom. It does not follow from the previous mini conclusion that you have. It does not follow from anything. So you can let, okay, you can actually let, if I don't have anything like this, let n is equal to 2m, that's okay. If I don't say m has to be an integer, so you can have n is equal to 2m for some real number m, this is still okay. But if you restrict this m to be some integer m, then it is not correct. There's no way that you can let. So this is not general enough. So you are talking about general n. N can be anything general. But for general n, any general n that you look at, it does not have this property, 2 equals to 2m. So you cannot let this. Okay. Okay. You can use let to define some new notation. Okay. So you can start something that does not against any of the premises of the conclusion, or you just use it for your convenience purpose. But you cannot let n is equal to 2m by introducing new properties to it. So you're adding n has to be an even number here. So of course, you add something new, then you might have a wrong reasoning afterwards because you're adding something. Okay? Okay? So it's like I can prove that all the things that I cook are very delicious. So blah, blah, blah. I say, okay, the sun rises on the east, and then the moon sets on the west, and then let the cooking of mine is delicious. Then my cooking is very delicious. Okay. Okay, so it doesn't make sense, right? So this is something that is wrong. Okay. Okay. Okay, now another one. So this is also a mistake. Okay, if x is real. So if x is real, then x squared is positive. Okay. So how do we prove? So there are two cases. X is positive, And then case 2, x is negative. Okay, if we are talking about case 1, x is positive, then we will have x squared is positive, right? If we start with x squared is negative, then we will have x squared is negative. Is that okay? So we have 2 cases, and then all the cases says x squared will be positive. So we are using proof by cases. So all cases, x is real, then x squared is positive. Okay, there's something wrong. What's wrong? Very good. So we miss a case. We miss a case. We miss the case that x can be 0. Okay. If we are missing the case x can be 0, so in this case, when case 0, let's call it case 0, x is equal to 0, then x squared is not positive. So this is positive. X squared is not positive, then this is not true. It is because not all cases will lead to the same conclusion, x squared is positive. So this is actually something wrong. And then this 0, when x is equal to 0, x squared is not positive. This gives us a what? This 0, we call it what? A witness? No, it's called a counter example. So this 0 is a counter example that all the square of x will be positive. It is a counter example. This is an example that says that this is wrong. We call it a counter example. Is that okay? Good. Okay. Okay, now, so we have enough about the mistakes. And then now, so we have learned a lot of tricks. So we have learned direct proof, indirect proof. If you have a statement that you want to show, try all the tricks that you have. Try all the tricks. And sometimes, if you have seen something that is similar, you can use it to help you to get a new proof. So for instance, I use this one. So we have known that square root 2 is irrational, right? And now, suppose that today I am asking you to show that square root 3 is irrational. Then, what should we do? Okay, of course we can. So we can search our memory to see if we have something proven to be similar. So here, to show that square root 3 is irrational, so we may look at, okay, check the text, check the slides, go to the web page, and check the proof of how to prove that square root 2 is irrational. And see if we can modify the proof a little bit to show that square root 3 is irrational. And it turns out that for this case, we are lucky. We can easily show that square root 3 is irrational. So the proof goes like, so let me quickly prove it for you. So we prove it by contradiction. So we assume on the contrary. So we are not assuming that this is, so we are assuming that this is false. So on the contrary, that square root 3 is rational. Is that okay? Now if square root 3 is rational, then what do we have? Then square root 3 is equal to p divided by q for some pq. And we can actually strengthen the choice of this pq such that they have no common factor. So if PQ have some common factor, we just remove the common factor, divide it from the top and bottom. Then we will have what? We will have 3 times Q squared is equal to P squared. We square both sides and move the Q squared around, so we have 3Q squared is equal to P squared. And then what do we have? We have actually showing that what? This is a multiple of 3 on the left-hand side. And on the right-hand side, it is P squared. So P squared is a multiple of 3. So it means that P has to be a multiple of 3. Does that make sense? Because if P is not a multiple of 3, then the square of P is 3k plus 1 for some integer k. We have shown this earlier in the class. So So again, 3q squared equal to p squared implies that p has to be equal to 3k for some k. If p is equal to 3k for some k, then 3q squared is equal to 9k squared. So if 3q squared is equal to 9k squared, then q squared is equal to 3k squared. Okay? Now if q squared is equal to 3k squared, q itself has to be a multiple of 3. So q is equal to 3 times l for some l. And then at this point, we get a contradiction. Is that okay? So this is extremely similar to the proof where square root 2 is irrational. Square root 2 is irrational. Here we are arriving at the conclusion that p has to be even. And because p is even, then we will have q is even. And now, for the proof of square root 3 is irrational, we are changing this. We set p to be a multiple of 3. We conclude this. And then we also conclude that q is equal to some multiple of 3 as well. And then we get a contradiction. Where is the contradiction?
No common factor.
Very good. No common factor and have common factor. Okay. So at the same time, we are saying that PQ has a common factor. And at the same time, we are saying that PQ they do not have any common factor. These two contradict each other. So we get a contradiction. Once we get a contradiction, proof by contradiction, this strategy works. So we will know that the first assumption at the very beginning has to be wrong. Okay? Okay, there is another type of strategy. This is also helpful in deriving new proofs for us. This is called backward reasoning. Okay, so what is backward reasoning? So suppose that I wish I have a better example, okay, but let's stick with this. Suppose that we want to show that 0.5 times x plus y is greater than x times y, let's say x greater than or equal to x times y to the power 0.5. Okay, this is what actually, this is something that we call the arithmetic mean is greater than the geometric mean, okay? Now, how do we prove this? So to prove this, so we are proving a certain statement Q. We want to show that Q is true. Let's say this is a certain statement Q. But somehow backward reasoning says that if we can show that P implies Q to be true and P to be true, then we can show that Q is true. Okay. Now, so look at it. So is that okay? So we know that this happens actually if and only if, what happens? If and only if, we can write it down as 0.25 times x plus y square is greater than or equal to xy. Okay, I'm writing this down. It doesn't mean that I'm showing this implies this. No, no, no. This is our target. This is our target. Let's say this is our target. But the target seems to be difficult to show. So in that case, I try to prove something such that if I can prove, instead of proving this target, I shift my target a little bit to prove this one. Because I know that this one implies this one. Is that okay? So assume that, okay, so we add a condition. Let's say x, y, they are both greater than or equal to 0. Okay. Make this better, okay? If I can prove this, then I can prove this. Am I correct? This implies this one. Is that okay? Of course, you will say that this also implies this one. But this is not our point. Our point is to show the target is correct. So instead of showing this target, I shift my target. So I shift my target a little bit. Let's call it target 1. So if target 1 is shown, then I can show that target is correct. Is that okay? Okay. And now I have a new target. And then to show that this new target is correct, I have another target. So I have another target, target 2. This target 2 says x plus y squared is greater than or equal to 4xy. Okay? And I have this new target. I will notice that if somehow, so we are doing things actually backward, if x squared plus 2xy plus y squared is greater than or equal to 4xy, then this one is true, then this one is true, then this one is true. Is that okay? And then if you look at it, this one is x squared minus 2xy plus y squared is greater than or equal to 0. This one implies this one. And then this one is x minus y squared is greater than or equal to 0. Okay. So in the end, we arrive at x minus y squared is greater than or equal to 0, and we know that this is true. This is true. Because this is true, then we know that this is true. And now because this is true, we know this is true. We know this is true, we know this is true, we know this is true, and so this is true. So in the end, this is always true. Okay? So although the target may be very far away from this original statement, if we do backward reasoning, we can shift our target a little bit to something that is easier to prove. This one may be hard to prove. We get something easier. And then from this easier thing to prove, we get something easier, and so on and so forth. As soon as we don't make it too easy, okay, so that we still have a chance to prove the final target is to be correct, then it works. Okay, so to do this, if we can do this, if we can do this, we can do this. If we can do this, we can do this, etc., etc. It is like solving a puzzle. Okay, sometimes if you want to open a treasure box, you need to get okay, let's talk about Mario. Okay, if you want to save the princess, then you need to play for 8 rounds or 8 worlds or whatever. And if you need to do this, you need to get a certain key, maybe to open the lock. And if you need to get a certain key to open the lock, you may need to go to visit a room one by one. And if you need to do this room one by one, maybe you need to get a special weapon or whatever. So you do things like this. So in the end, you will know that in order to save the princess, then you can do this, and then you can do this, and then you can do this, and so on and so forth. So this is the so-called backward reasoning. So you don't start from this one at the beginning. You try to check if going backward a little bit can make your day easier. Okay? Okay. Okay, now, to end the class, let me give you 3 interesting examples, okay? So this standard chessboard is what? Is 8 by 8 square, so you have 8 by 8 square. Okay, 8 by 8, 1, 2, 3, 4, 5, 6, 7. So it is an 8 by 8 chessboard. Okay, and then let's say we have some domino piece of this size, 1 by 2 or 2 by 1. So you have infinite supply of this type of domino pieces. So it's called domino, okay? Domino, okay. So why is it called domino? Okay, mino, okay, I don't know. Do means 2, okay? So you have trinomials. Trinomials, I think, okay. So these are something that each piece you have 3 little squares joining together. And now we have domino. And then we want to ask, can we use dominoes to cover the board completely so that no 2 domino pieces overlaps each other, and then each of the square can be filled? Is it possible? Yeah, this is super easy. Yes or no? Yes, very good. So how? You have 2, 2, 2, 2, 2, 2, 2, 2, 2, 2. Is that okay? Okay? Okay. Now, how about I remove this square? Just 1 square. Can we still do this? No? How can we show? How can we show? Now, the rule is that no domino can overlap with another one. So there is no overlapping. But we need to cover every piece every square of this chessboard, right? So we can get a contradiction because the total number of squares we are covering should be an even number, right? But there are only odd number of squares here. So we should not have some domino that is outside this board. Okay, we need only to cover. Okay, this is the rule actually. So in that case, we have a very easy proof that this does not work because there are odd number of squares here. But if we use domino to cover, then it has to be even. Okay. Now how about this one? If I remove one more square, can we cover every square? Yes. Yeah. So simple, right? So we have 2, 2, 2, 2, 2, 2, 2, 2, 2, 2. We make everyone lying down. Now, this is tricky. If I remove the opposite corner, does it work? So I tell you, this cannot. We cannot. But we cannot use the previous proof either. It is because in the previous proof, we are using the odd number of squares. Here, there are even number of squares. So we still cannot do this. But to prove this does not work, so, okay, anyone has heard of this question already? Okay, good, excellent. So we try to add more information into this board to help us. So if you remember a chessboard, so chessboard has how many colors? 2 colors, right? So this, let's say this is a black, this is a black and white, they are alternating, right? 1, 2, 3, 4, 5, 6, 7, I have one more. Okay, I should remove this one and then remove this corner. This is what I should. And then this one. Okay, let's do this more quickly. Okay. Okay, thank you. I'm drawing a 9 by 9. Am I correct? It looks like. No, this one is this one. Let me see. 1, 2, 3, 4, 5, 6, 7. Oh, I have one more. Okay, this one. So I'm drawing a 9 by 9. Okay, it should be 8 by 8. And then without this one. Okay. This is now how the chessboard look like. Is it? Now if a domino is covering any 2 pieces, they has to be neighboring. Okay? So you can think of this domino piece is of this form. It must have 1 white and 1 black on each domino piece. Okay, how does that help? So how many squares are there? There are 62 squares here. All right? How many of them are white? How many of them are black? There are going to be, in my example here, there are going to be 32 blacks and then 30 whites. Is that okay? And this is a proof. Because if we are using domino pieces to cover, then the number of blacks and the number of whites have to be the same. And now they are not the same. So this does not work. Is that okay? Okay, I hope you like this example. Okay, so on Wednesday, we will talk about induction. Okay, thanks a lot.